Good morning, Professor. This is my second project in this fall semester. This project is about the create 3D human form point cloud data. We just use the point cloud data and then generate into 3D human form. So here is an outline of my work that we are gonna talk in this presentation. Introduction, problem statement, objective, methodology, result, challenge and limitation of this project, and future work, and the last thing is a conclusion. Okay, for the introduction, in this project, we use the XAvatar GitHub repo and it generates the 3D model from the 3D point cloud data. This model is a combination of the SMPLX and XAvatar or XHuman dataset that scan from real human. It uses SMPLX as a backbone of the model and use the human avatar to be the skin of the model. We are testing only three demo motion sequence in this project, which are ballet dance, emotion, and tennis. So for the problem statement, according to the previous work that I've been doing in the last month, we can get the x coordinate, y coordinate, and z coordinate of the human model. But the problem is whenever it have the occlusion, for example, for this one, this is the prediction that is might correct, but sometimes we lose some part of the human part and we cannot recover it by the recent technology. With the heat map scanning, we cannot determine everything. Even we are with the RGBD camera, we cannot get the overall body part from the video or from the data point count because this part, the left arm is gone, so we cannot get it back. So we need something to navigate us to get the human body, which is SMPL that I'm gonna talk about. Objective for this project, we're gonna create the replicate of the human pose from the RGBD camera. We have the input from the RGBD camera and 3D scan, and we're gonna use those input to generate 3D human form. This process aims to capture the complexity and nuance of the human autonomy and the movement of digital format. By utilizing the RGBD data, the method leverages the color information combined with the depth sensing to understand the shape and spatial position of the human body. Overcome the limitation of the existing model is a developed XAvatar is comprehensive to understand digital human avatar model by capture not only the body but facial expression, hand gesture, and the appearance of the human, which can contribute in the VR and AR industry in the future. So here is the method for XAvatar that create from following. Okay, first they start with the input pose and the texture scan, which is accompanied with the SMPL registration. And you can see that the first one they detect the GLH, which is left hand, and then they detect the GRH and GB. GRH is the right hand, GB is the body, and GF is the facials. So they can detect 4 parts. They initially focus on the sampling point in the way that the sensitive the difference of the body parts. The result is in denser sampling for the smaller part like the hand and the face, which they focus as a different part from the human body. They greatly improve the model quality by this area. For the sampling point XD, which we can see from here, they find its corresponding in the canonical space, which is XC. This is done using the iterative root finding algorithm that addresses the forward scaling equation with the continuously learned skew weight. This process called deformer network. The deformer network is especially initialized with the bond transform related to the body part of the sampling XC. For the next approach that they do, they put the deformer network and go to the next step, which is the final shape. They use the occupancy network to output the 3D human form. Once the output from the occupancy is obtained, they calculate the normal and integrate them with the final correspondence with the canonical space, which come from the XZ. And they use the input pose. The occupancy last layer feature will include the input pose, facial expression, and hand gesture, and they merge together into the texture network, which we can see at the last one. The texture network is designed to predict the final color, which we get it from the texture scan. Okay, let's talk about the animation. So the animation gonna have two parts: scanning body. The first part is gonna be RGBD data. RGBD data is gonna be on this size. So RGBD data will be used only one camera, but they try to capture overall body part by using the camera. Only one camera to capture the whole body part, and then they try to register the 3D point cloud of that body part and try to create the SMPL, which is the backbone body for the human 3D. And the second one is a 3D scan. You can see that the human subject just stands still, and they have the 53 depth camera pointing to that subject. So which is more accurate than RGBD data. By the way, in this experiment, I'm gonna process the input both from the RGBD data and from 3D scan. In this project, we will use the model to train and visualize for 3 scenarios, which use the motion extraction from the Pimax X. And this input data is come from the monocular RGB video. So the first scenario is playing tennis. You can see on the top one right here is the playing tennis. And the second one is a ballet dance. And this one, we have the input lady dance ballet. And then we just extract it and then put into the SMPL model. And each model can perform something like this, which we're gonna present in the next one. Okay, for the dataset, after I get the permission download the XHuman from their website, so they provide us the dataset for the 20 subject. So the subject number is right here, 0016, 0017, and so on until the 00888. Every subject is come with the high quality texture scan SMPL X registration. So it's have 100% 3D landmark in every things, including the body pose, hand gesture, and facial expressions. So it's have so many emotion, including the clothing type, hairstyle, and gender, and age. So basically, this dataset is contain everything that we need, and those dataset will available for me to download within 72 hours. I already download like 10 of them, and it's cost like 40 gigabyte by overall. Yeah, I successful doing this training. For the X Avatar training, after spending time with them for 3 weeks, I talked to the team of X Avatar and tried to modify my library to work on my PC, which run on Linux. This is the problem when we run on Windows. This library doesn't work at all. But when we move to Linux, everything works fine. So we successfully run training last week, and we make it work with the ballet dance packet. This packet generates SMPL 3D human data in ballet dance, which we can use it as a cartridge. Each iteration will use the ballet dance 3D skeleton and generate into the subject. So each file will be the subject file. For example, this subject 00885. So this one will generate as its human pose and human action. So each subject have different length of the arm, length of the leg, and length of the body. So we need to train it. To use the ballet dance, we can put any 3D skeleton to them. Let them learn how to move it continuously into one video. Okay, for this one, with the 907 iteration, which equivalent to 907 point cloud file, and it's used around like 1 hour and 18 minutes to train it. And each PLY file, each point cloud is contain the coordinate XYZ 3D coordinate of each landmark of the human body of that subject. It's generated by the OpenPose. The computation uses, I'm using GPU RTX 3090, which use like 40%, and they use a GPU RAM for 22 GB RAM out of 24 GB RAM. The CPU uses 64% of the time, and the RAM usage is 23 GB. So after I'm learning this SMPL model, we could develop this program to use with our own dataset in the future. If we can extract the PLY file from the Intel RealSense camera, and then we can put it in this model. We can train the model to follow our action, any action that we want. For example, the action that I have done in the previous project in this semester, which is 3D human estimate. This one we can generate in the PLV file, and then we can put any action that we have into here. For example, like a truck bending and the squat or anything that is shown in the here. We can generate it into the PLV file and then train it. So after we train it, we cannot display it yet. We need the XAvatar visualization to convert the 3D information data of that subject into the video. This one is the output, is the one, is a 2D output instead of 3D output. So this one we can upload into the MPEG-4. So it take around like 5 minutes 23 seconds convert the 3D point cloud data into the video, and it take like a 23 seconds here to render that video into the MPEG-4 file. Okay, and this file is equivalent to 1814 frames. The video run at the frame rate 60 frame rate per second. So this video of the ballet dance will have around like a 30 seconds for this video. Here is the example of the ballet dance. So this model generated from the SMPL, the action pose is .ply file, aka 3D point cloud coordinate. You can see that it works smoothly, and we have the shadow, we have everything. We can reduce the occlusion. We can reduce the occlusion from this method. And so the next one, this is the ballet dance. I generate each model. So remember that one model I need to spend time with one subject for 1.5 hours to generate only 30-second video. So the ballet dance on each subject is working fine. But some of them, for example, the subject 0020, you can see that the facial expression is not that good, but the finger and the hand, everything is looks so good. The body is look like a perfect. So this one we need to improve in the future and make the facial expression look like the original subject. And the next one is the emotion. This is the second scenario that we have. This emotion is take like around like a 302 iteration. 332 iteration is equivalent to the 10-second video. So this is focused on the facial expression, which is not 100% accurate. You can see the mouth look black when she open the mouth, when he open the mouth. So we may need to scan the inside the mouth, so it may look much better than this. And you see the leg is keep folding, the hip is folding, and the leg is not stand still. We may need to adjust it and make it to touch the land. We need to create the synthetic ground for this human subject in the future to make it more accurate. The third one is a tennis playing. So we can see that like everything looks smooth, but not that good. The feet is not touching the ground. We have subject 0027 3D scan, 0034 3D scan, 0085 3D scan. And just let you know, each subject use time to train for the tennis we use half an hour, for the emotion half an hour, and for the ballet dance each subject we use 1.5 hours to train it and visualization it. So this project I spent time more than 15 hours for the training and visualization, because we have another model that we train and it failed. And we're gonna talk about it in the next slides. So this is the one that we fail. Not every subject that I choose and then I train it and visualize it looking good. You can see that not every subject that we have done and is go correct. So for the left one is the tennis. You can see that the human body should facing the front, not the back. And the leg is looks so weird because it's facing backward. And it's used the back to facing the camera, even the hand. This is the wrong side SMPL that we generate, and we think that we can modify it by flipping the SMPL human model first before we export it. And this is the error that we found on the right hand side is the dance. You can see that the dance one looks so weird. The hand is flipping on another side, and it's very hard to see the face because they use the back head to look at the camera. It looks like a ghost. So this is the error that we found while we generating the 3D model, and this error is come from RGBD camera only, and you can see it here. So coming to the evaluation, we use a chamfer distance, which is measurement with a millimeter. So for the X-Human 3D scan, it just have the deviance 5 millimeter from the original subject, and for the emotion, it have 4 millimeter from the ground truth or the original subject. And for the tennis, and we have the overall landmark that is chamfer distance 5.72 millimeter away from the subject. For the IOU, so we try to merge the SMPL model that we generate and with the ground truth, and the IOU is the 90%, 91%. For the RGBD, this is a real problem that we don't have enough time to fix the model to work. So all of them are invalid value to the evaluation table. So in the future, we may need to adjust the RGBD model to match with the evaluation, to match with the size of the human subject, and try to create it better than this, and then we can evaluate it. For the challenge and limitation, so the RGBD dataset from the X-Human is hard to visualize. We need to flip the subject 180 degree turn around, so we can get the correct proper human body. And for the device limitation, even we have the one RGBD camera, we thought that it's not enough, it's not sufficient to do this project. It may encounter difficult to get the landmark, the hidden. So we may need at least 2 RGBD camera in the future to create the dataset, something like this. Okay, the future work, we're gonna use the camera to create the manual dataset from RGBD camera and contribute this X avatar in the future in our own dataset. So this way we can contribute other projects in the medical or maybe in the AR VR world industry, anything that we can monitor the disorder human children, or we can create the ground truth for each action accurately. And in the future, we can develop this one into the children human body. Okay, the next step that we're gonna do in next semester, I'm gonna use the multiple camera with the RGBD into the system, so we can reduce the occlusion, and then we can generate more accuracy ground truth. Once we have the accuracy ground truth, we can train it and find the accuracy percent, IOU, and anything that we can contribute to work in the future, and we can train the model to make it more efficient than this. Okay. Anyway, thank you for listening me, and I hope you enjoy this presentation. All right, have a good day, sir.